Cool. Right. So before we get into this efficient verification, we need to kind of understand what preconfirmations are. Preconfirmations is this new idea where you know the next 32 to 64 Ethereum proposers, and they can opt into additional services apart from like just proposing a block. They can sign up, say a message saying ahead of time saying like, hey, I will include your transactions in 5 blocks when I'm the proposer. And they can do this, and this topic is being researched into in base rollups and trying to make um, sequencing for base rollups like milliseconds instead of like seconds. It also is a very easy way for rollups to decentralize. In some sense, you have a centralized sequencer every slot of Ethereum, but it keeps rotating between them. Um, yeah. So this diagram is from Justin Drake's initial post on base preconfirmations. Um, right. What we do is we modify this scheme where a user requests a preconfir, which is basically a Ethereum validator, like, hey, include my transaction in n blocks. We change that relationship or that commitment from inclusion to verification. So we request a proposer to verify a proof by in block in slot n plus 2. And then the preconfir or the validator signs a message saying like, hey, I have verified that your proof is vpi, right, which is a verification of pi. And I will include this result in my block in slot n plus 2. Right. How can this fail? So there's 3 ways this can fail. First is liveness, right? The proposer at slot n plus 2 doesn't propose a block at all, and then you did not get your guarantee was not met. The second is safety, where the proposer did propose a block at slot n plus 2, but did not include your transaction. In this case, you did not get your proof verification. And the last one, which is actually an extension, like the first 2 are just from like vanilla preconfirmations. The last one, which is correctness, which is where a proposer signs a proof verification which is incorrect. Basically, let's say they sign on a proof that this is false, but the proof is actually true. And in that case, they should be penalized. Actually, in all these 3 cases, they should be penalized because they lied. Cool. So we will now see how we can use the Ethereum pipeline to do efficient verification on Ethereum itself. In general, like, to give you like a high-level overview of how Ethereum's consensus works, there is a bunch of validators, as you can see, committee A, committee B, and there's a few aggregators. Basically, these validators in these committees are signing on a block, right? So they re-execute a block, they sign it saying like, hey, I have verified that this block is correct, and then some aggregators, like some of those signatures, usually BLS signatures, into one BLS signature, and then the beacon chain nodes can verify like, hey, I know that 2/3 of Ethereum nodes said this is the correct block. Right. We exploit this part, and we basically, this is the offensive part, which is we use optimistic execution for verifying ZK proofs. Basically here, instead of all Ethereum validators verifying a ZK proofs, we have one Ethereum validator verifying a ZK proof, and the other ones are like tasked with the responsibility of challenging it. Why is this more efficient? This is just a simple system design thing, right? In the first case, which is supposed to be like consensus, where we have the red circle, which is the proposer. He makes a block. He sends it to the other validators, and then they re-execute it and say like, yeah, this block is correct. Here, I'm signing on it. In optimistic verification or in optimistic execution, the proposer just sends, hey, I've done this execution, and in the good case, the other validator just sign this. Yeah, this is correct. Ideally, they should check and they should verify that this is the computation done. It was correctly. But in the good case, it's compared to like the current certainty of Ethereum, which is like 1 million validators executing the same thing. In the good case, we will only have one validator or a handful of validators executing the verification of our proof. We will look into later how we can make sure that this is correct and how can we verify, how do we make incentives so that the proof verification is always done correctly. This technique can also be used for faster finality for rollups. So in the current world, verifying one ZK proof on Ethereum is kind of expensive, and it's very expensive if we want to do it for each rollup block. So what rollups do is they aggregate their proofs, either like folding schemes or recursion or whatever. But it usually looks like they have like, let's say, pi 1 and pi up to pi 4 represent proofs for blocks 1 to 4. What they do is they make new proofs, pi 5 and pi 6, which aggregate the proofs from pi 1 and pi 2, and pi 3 and pi 4, and then they make one final one which aggregates those recursive blocks. By verifying pi 7, you can verify all those proofs, pi 1 to pi 4. And what you do is basically amortize the cost of verification of one proof across all the proofs, right? This is really good for like cost effectiveness, and this is not really good. It's kind of needed right now. If rollups didn't do this, they'd be more expensive than L1 possibly. Um, but what this does is adds a lot of finality time, because let's say block 1 was done and pi 1 is calculated, but the proof for pi 1 now needs to wait for pi 7 to be calculated to be verified on Ethereum. And what this kind of adds up to is, let's say, if all the leaf proofs take t seconds, and then the first stage of the tree takes x seconds, and then the last stage takes y seconds, the overhead in the end is 4t plus 2x and y seconds. That's just the proving overhead, and then it needs to be verified on Ethereum. And what this results in, or what the experience we see today, is that ZK rollups have a finality times of like up to 6 hours or 12 hours. And we can change this if the verification cost of proofs would be cheaper. Optimistic verification, in my opinion, kind of helps here. Multi-proof verification, right. So this point is about how we have different rollups using, or co-processors using different ZK proof systems. We have some using Halo 2 or Plonky or Starks and across, right? The problem is you can't efficiently aggregate proofs across these proof systems because they use different prime fields, they just use different architectures, and it would take like years of research to actually figure out, either we first consolidate to the same ZK system, or we like figure out new prime fields or new ways of like doing aggregation across all these different proof systems, which I think if you do naively, it might cost more than just the leaf proofs themselves. But with the execution precons, what we can do is just ask the validator, send the leaf nodes, right, pi 1, pi 2, pi 4, to the validator, and say like, hey, verify these in your transaction. They verify them off-chain, right, run C++ verifiers, and just include the results on-chain. So we got verification for multiple proofs in one transaction, but we didn't have to do the overhead of actually making more proofs. This is also super useful because we now do less computation overall, because we don't need to calculate pi 5, pi 6, and pi 7. We can just calculate the leaf proofs. This is really cool for prover networks, where they're all looking into how can they do recursion, and they can do these aggregation techniques across all these different jobs. But what's really hard about them is estimating how much time it will take. Like, think of it as a market where like a bunch of people submit proofs, and they want one proof in the end. The problem is that now this network has to manage all these proofs, and it has to figure out what time is most optimal to scheduling. Basically, it's a scheduling problem where pi 1 might need to wait 5 more seconds for pi 4 to be generated, which means that pi 1 is paying the time cost of pi 4 as well. Using optimistic execution, we can do greedy aggregation. We can just say, whichever proofs are ready right now, just send them right now, and then the next batch can go when they are ready. Right. So now this is the interesting bit where we look into how do we make sure that the validators can't lie. So we use something called fraud proofs here. And who can submit a fraud proof in this case? The two questions that are important are who can submit a fraud proof and what is the challenge period. So who can submit a fraud proof? Anyone. It's permissionless. It's just verifying a proof on chain. It's what we do today. We just run a solidity verifier, and it tells us the result. What is the correct challenge period? I think this needs a bit more analysis, and I'm still working on it. If you have any thoughts, I would love to hear them. But I'll give you some initial thoughts why I think this is better than the current status quo of optimistic rollups. Cool. So this is kind of the pipeline that I imagine that would fold out with verification precons, where we have a user who wants to verify proof pi. They send their transaction to this pre-confirming validator. So it's a validator who signed up to the service saying like, hey, I will verify proofs for you, and if I do it correctly, then I should get paid. If I do it wrong, I should be slashed. The prover, basically, the validator has a choice that, do I want this reward? If so, I will basically do this proof verification for you on chain. And then at the top, you see they sign a receipt saying like, hey, I will include the result of verifying your proof on chain in block B, and sigma is the signature. So you can basically make sure that you can hold them accountable for it. So here we see that actually we get verification, or like we get soft finality really quickly in some milliseconds, because the time it takes for the validator to sign the message above is probably a few seconds. They verify the proof off chain, and then they just sign the result. So at that point, you know the validators have already committed to what they will include on chain when their block comes. So the prover already knows the result of the proof, right? They can also run the verifier, and it takes like a few seconds or a few milliseconds, and they can be like, hey, I see that the validator, pre-confirming validator, committed to vpi, which is wrong. Maybe it's false. And then you can just instantly, as soon as they pre-confirm, you can actually go to another validator and get your challenge transaction pre-confirmed. So you can have like sub-second challenging and verification. But this also means that the incentive for the validator to lie is super low because it's super easy to check that they lied. Because what if, in this case, compared to optimistic rollups, we don't have to generate a proof to challenge them. The proof is already there. Pi. We just need to verify it, and verifying proofs is really cheap. Um, cool. So I think for these reasons, the challenge window of this system can be probably a few blocks, or maybe like at max 2 epochs, which is like 12 minutes, which is still better compared to optimistic rollups, which is 7 days, or for ZK rollups, where the finality currently is like 6 to 12 hours. We can get down the finality of ZK rollups from 7 or 6 hours or 12 hours to 12 minutes, which is quite a nice step change. Um, cool. So what does the system look in the end? And this is just the extended diagram. What happens here is that we have some validators who've already pre-confirmed that they will do the service. Users go to them directly saying like, hey, verify my proof pi, and for doing this, you will get dollar amounts of money. If the validator chooses that, hey, they will do this, then what they do is when the block comes about, they make sure that before including the user's transaction that includes the proof, they include the transaction which includes the verification of that proof. And it's kind of like a dictionary, right? Basically, they front run the user's proof transaction with their verification transaction, and then that's how we know that this proof was verified on chain. They also sign a receipt saying that, hey, I will do this, so that if they don't do this, we can hold them accountable. And I think that's it. We are working on like a work in progress implementation. The system is actually quite easy. It's a few smart contracts and a few sidecars that an Ethereum validator will run, and this will allow them to do this verification, make some more rewards, and provide new services to the Ethereum ecosystem. Any questions? Yeah.
So what happens in case of reorg? So does it lead to this liveness fault, but it's not the validator fault that his block got reorg?
Yeah. So the question is, what happens if the chain is reorged? Basically, the validator was true. It includes this transaction, but it reorgs. So that's a really good question. What should happen? I think what should happen is that there's systems basically where we can prove to the smart contract that the chain reorged, because you can show that there was two forks and the validator was voting in the correct fork. They were reorged. We can also use external finality gadgets. So some different chain could basically record the finality, right? And let's say we can use Nethermind for that chain, and it records, hey, I verified these proofs, and even if Ethereum reorgs, you can bring those results back to Ethereum. In my opinion, reorgs here is less of a problem, and is probably a system of Ethereum as well. We can kind of work for single soft finality, where rollups are supposed to be derived from Ethereum, in my opinion. So if Ethereum reorgs, the rollup should reorg. Yeah, I agree that we should. It's bad UX, but this is the definition of a rollup, in my opinion. If the rollup has its own finality layer, then it's closer to a sidechain. Do you have a question?
Yeah, I'm not sure I understand like the setup when you say the user wants to verify proof pi.
Uh-huh.
So in my kind of mental picture, we have like if we imagine this in the rollup context,
Yeah.
then it is the rollup that generates the proof for the validity of all the transactions. And
Yeah.
then is the user supposed to be a rollup operator or?
Yeah, the user can be like anyone. It can be a rollup operator, it can be a co-processor, or it could be a user-facing app as well. It could be like a decentralized identity solution where the users generate the proofs like locally on their browser, or it could be a rollup. It could be anyone really. Yeah. Yeah.
May I ask a question? Like, what does the V of pi look like? Like, is it some data structure? Like,
True or false? Like, it's either true or false. It's Boolean.
okay. So it's just basically the validator signing
Yeah.
Boolean value.
Yeah.
Okay, I checked and I see its value.
Yes. Yeah. And the important thing to notice here is that the proof, like use Ethereum for the data availability. The proof is still available on chain, so that people can challenge it. If we do this completely off chain, right, where like the validator verifies it on chain, just puts the result down, that's not good enough because he could hide the proof himself, and then no one can challenge it. In this case, the proof is on chain, so everyone can see, hey, this is the proof, and now they have incentive to challenge. Naively, I would say, going back to this slide, naively, I think the cost of this, like let's say it costs 300,000 gas to verify your proof on Ethereum right now. Naively, I would say this should cost like 1/1,000,000, 300,000, because Ethereum has 1,000,000 validators, and your gas is paying for all validators to run the transaction. In this case, only one runs it, so it should be like 1,000,000 times cheaper. I think more work needs to be done where you basically need to incentivize challenges as well. So you need to be a bit more than just the cost of one validator verifying it. You need to kind of account for what would the challenges make. It's like a repeated game. If I keep playing this game over 2 weeks, what is my expected payoff? So you can encode some error value and say like, hey, you pay by this much margin. So you incentivize challengers to challenge it. Cool. Any other questions? Cool. Okay. It seems like everyone gets it, and everyone's going to be implementing their own versions of this tomorrow. Look forward to like a billion implementations. Thank you.